Okay, good evening everyone. I am Shivani Dhok and I welcome you all for the week 6 tutorial for the course of Modern Digital Communication Techniques. And like every week, I'll start with the recap of the week 6 content and followed by some questions related to them. Okay, so let's start with the recap of week 6 content. So this week was entirely based on the modulation techniques, digital modulation schemes. And the details regarding this were discussed, and also how to label each constellation point and which is the best possible way for these uncoded systems to designate or give the labels or code them or assign them a constellation point or map or have a proper symbol mapped from your symbol to your waveform. So that thing was discussed in this week. So this week started basically with your pulse amplitude modulation, the first technique, that is this pulse amplitude modulation technique. And basically what this technique does is, if I have this line, let's say this is some some axis which corresponds to the basis, and this is 0. So this will basically create multiple amplitude levels, that is pulse amplitude modulation. So these amplitude levels, like this one, this one, this one, this one, and this one, these amplitude levels will correspond to one of the beat sequence that we are considering. Like and the signal which corresponds to let's say mth symbol or mth combination is given as real part of AMGT 2 pi FCT, and this thing can also be written as AMGT cos 2 pi FCT, where this m varies from 1 to till capital M, and this t, this signal is valid only for a range of 0 to t, where this t is given as k times tb, and this tb is the bit duration, and this t is known as the symbol duration. Okay, and this am is basically given by this formula here, that is 2m minus 1 minus md, and d is the distance between adjacent amplitudes, or to be precise 2d is the distance between the adjacent amplitudes. Then the energy for this signal, for this pulse amplitude modulated signal was calculated, which came out to be half am square eg, where eg is the energy of this gt signal, that is the pulse shaping signal, where this eg is basically integral from minus infinity to infinity, or to be precise, since the signal is only restricted to 0 to t duration, this is 0 to capital T magnitude of gt square, or if it is, anyway it is a real signal, so instead of magnitude I can just write g square t dt. Now this SMT can be written in the can be represented using orthogonal basis, like something like this, where this SM is a coefficient which is equal to Eg upon 2 AM, and this Ft is the basis vector which is under root 2 Eg Gt cos 2 pi FCT. I'll take an example of how this basically comes out, and it will be much more easier and clearer for you how this thing is coming out. Then the Euclidean distance between two constellation points is given by this formula here, that is d under root 2 Eg under root m minus n. I think this is also inside the square root. And d min, that is the minimum Euclidean distance. So this thing here, this thing is basically the minimum Euclidean distance. Okay. After that, a labeling was discussed, like how to give, like, okay, suppose I have k equal to 2 bits, that is I'm grouping. So what exactly is happening is I'm having some bit stream which is coming to my modulator, and what I'm doing is I'm combining these k bits, and each of these k bits are being mapped to a waveform. This is happening, and the number of distinct waveforms, which are these m, is basically 2 to the power k. So suppose I have k equal to 2, so my m will be equal to 2 square, that is 4 amplitude levels I'll have, and these four will be one will be plus D, then minus D, 3D, and minus 3D, and the possible combination of these two bits are 0 0 0 1 1 0 and 1 1. So how to designate these four possibilities to all of these signal or constellation points? So the criteria to do that is, so when I am decoding, which will be discussed in later time, so I'll be having certain decision regions. So the decision region for this 3D minus 3D will be this one, this one. Similarly for this minus D, it will be this region. Then for plus D, it will be this region. And for 3D, it will be this region, the remaining one. This one. Okay. So, and it was said that along with the received signal, what do we have? We have an additional noise. So it may happen that the signal which I am receiving, or basically what I am receiving, let's say is what I am sending is this quantity. However, I am receiving a quantity which is lying here. Or let's say I have sent this quantity, but I have received something here or something here, which means that there is a possibility that whatever I received lie in someone else's decision region. So if that is happening, and consecutive decision regions bits are uh, are varying for more than one value, then my bit error rate will be higher. So in order to reduce the bit error, what we do is these consecutive regions or these consecutive constellation points are assigned those bit streams which vary only by one bit, and that thing is given by gray coding. So for this thing, what we can have is 0 0 assigned to minus 3D, 0 1 assigned to minus D, 1 1 assigned to D, and 1 0 assigned to 3D. So we can clearly observe that this and this varies only at this place, the first place, that is the LCD. Similarly, this and this varies only at this place. These two vary at this place, and so on. Okay, so this is a better thing that, and anyway, it is much more possible. It is that a constellation point or a constellation point which I am sending is, let's say it's this one, so it's higher possibility that it will be here, or it will go what will be received will be in this region or this region. It will be less likely to be getting in this region. So that's why we are more interested in assigning properly the things to the consecutive uh, constellation points. So that is the gray coding that was discussed. After that, another phase shift keying another modulation technique was discussed, which is known as phase shift keying. And the signal for this phase shift keying is given by the real part of gt into e power j theta m 2 pi fct, where this theta m carries my message information, which is given by 2 pi by m into small m minus 1. Again, this m varies from 1 to capital M. This we can write as gt cos 2 pi fct plus theta m, and this can also be written as gt cos theta m cos 2 pi fct minus gt sin theta m sin 2 pi fct. This thing can be written in the with the help of orthogonal basis as sm1 f1t plus sm2 f2t, where this sm1 is given by this formula, sm2 is given by this formula here, and f1t is the first basis that we have, which is depending on this cos, which is a function of this cos, and f2t is the second basis, which is given by this formula here. The energy is given by Eg by 2, and the minimum Euclidean distance, the Euclidean distance between the m and nth point, constellation point, is given by this formula here. So this is the Euclidean distance that we are looking at. That's why we are having a superscript of E. I hope that is clear. And how does this constellation look? So this constellation is a two-dimensional constellation. So let me write it precisely. It is a two-dimensional constellation. Then this is the first basis vector, that is f1t, and this is the second basis vector, that is f2t. And this is a circle, and the radius of this circle is under root Eg by 2, and these constellation points lie on this circle, something like this. So this is how a typical PSK constellation looks. After that, the third modulation technique was discussed, which is known as quadrature amplitude modulation, and that is represented by this signal, which is AMC. This AMC is the amplitude associated with the cos minus AMC GT cos 2 pi FCT minus AMS GT sin 2 pi FCT. This can also be written as the real part of this complex quantity, which is AMC plus J AMS into GT into e power j 2 pi FCT. And this can also be written as Vm e power j theta m e power j 2 pi FCT and real part of it, where this Vm is under root of AMC square plus AMS square. Let me write it properly. This Vm is under root of AMC square plus AMS square, and this theta m is tan inverse of AMS upon AMC. I hope this is clear. And then we had looked at how can we represent it in terms of bases. This is very similar to what we have done for PSK. And again we have SM1 as this quantity here. You can clearly see it from this quantity. And SM2 as something like this. And the basis vectors are again the same for both PSK and QAM, and the minimum and the Euclidean distance between the M and nth constellation point is given by this formula. Now it was also discussed that this QAM signal can be viewed as a PSK and a PAM signal, as a combination of PSK and PAM from this formula. So this thing will correspond to different phases which I can get from a PSK constellation, and this Vm I can get from a PAM constellation. And we can set these two independently. That's why we can construct a QAM signal by taking a PSK and a PAM signal. Another way of doing this is do pulse amplitude modulation, that is PAM, on both I and Q components, that is in phase and quadrature. So by convention, this cos component is referred as in phase, and the sine component is referred as quadrature, and the in phase component is this AMC and this quadrature component is AMS. And again we can independently set these two, and by setting these two, what we are doing a pulse amplitude modulation along this basis vector, and another pulse amplitude modulation along the second basis vector. Another thing that was discussed was this square and rectangular constellation, which is basically obtained from doing pulse amplitude modulation over both I and Q components individually. After that, the scalability of QAM was discussed. So what does the scalability mean? If I need to add more constellation points, I can do that without disturbing the existing constellation. This helps when we want a dynamic change in the constellation size. This was all the content that was discussed in this week. And after that, if you have any questions, please let me know. Else I'll go ahead and start solving few questions. Okay, if there are no questions, then let's start to solve. Okay, so this is the first question that we are having here. It says that a symbol stream contains alternate QPSK and 16 QAM. What do we mean by QPSK? It means that Q means quadrature. So it means that I am having 4 constellation points in a PSK, something like this. Okay, so I am doing MPSK with M equal to 4, and this is 16 QAM. So I am doing M equal to 16 QAM here. So what exactly is happening is, what I am transmitting is something like this. I'll send a QPSK, then I'll send a QAM, then again I'll send a QPSK, and I'll send a QAM, and so on. And this QPSK is of M equal to 4, which means that the K required for this, the number of bits required for this, is log 4 to the base 2, which is 2, and the number of bits required for this is K equal to log 16 to the base 2, which is 4. Okay, so this is the information that we get from the first line that is given here. Then it is said that if symbols are generated at a rate of 1 Mbps. So what we have been given is symbol rate is 1 MB 1 mega symbols per second, and we need to find the uncoded or raw data rate. So what does this mean is, we need to find what are the number of bits I am sending per second. Now what exactly is happening here is this rate which is given here is the rate for this stream. So this rate for this stream. Now suppose there was only QPSK. Then for each symbol I was having 2 bits. For each symbol at that time I was having 2 bits. However, now I am having 2 different constellations of 2 different sizes which I am sending consecutively. Like each symbol, like what exactly is happening is, each symbol is not having the same length. For example, this is having a bit length of 2, this is having a bit length of 4, which means that the bit length for, corresponding to each symbol is not same, and that's why we will need to take an average length or average bit length. So this raw data rate is basically bits per symbol multiplied by symbol rate. Okay, and this thing is an average thing, because my symbol rate is changing, my bit size, my symbol size, or the length of the bit stream is changing with each symbol that I'm transmitting. Like this QPSK has 2 bits, this QAM has 4 bits. Therefore, this average thing is basically equal to 4 bits, which correspond to this, plus 2 bits, and these 2 number of bits, like these 4 plus 2 bits, I am sending for how many symbol durations? 2 symbol durations. That 4 plus 2, 6 bits are basically corresponding to 2 symbol durations. Therefore my average bit per symbol thing will be 4 plus 2 by 2, which comes out to be 3 bits per symbol, and therefore raw data rate is 3 into 1 mega, that is equal to 3 megabits per second. And this question was asked in gate 22. Any questions? Please feel free to unmute yourself at any point of time if you have any questions. You may stop me at any point of time. It's fine if you don't wait till the end to ask your doubts. Okay, so if there are no doubts, then let's go ahead with the next question. So the next question says that we need to perform gray coding based mapping for this 16 PSK. Okay, so what does gray coding say? That consecutive binary symbols should vary by only 1 bit, as discussed earlier. So this is what the gray coding is saying. And see, we have here k 16 PSK, which means my M is 16. I have total M symbols, and number of bits k is log 16 to the base 2, which comes out to be 4 bits. So basically what I need to do is need to construct 4-bit gray code. Okay, so let's do that. So let's start with our convention and start with this symbol, this constellation point, which is located here. So this is 0 0 0 0. Okay, before doing that, this thing that I have plotted is basically my constellation point, and each of this point, let's say I take this point here, this point, and the angle that it makes with this horizontal axis is theta m, and each of this point is basically root eg by 2 cos theta m, comma root eg by 2 sin theta m, and this comes out from this formula here, this one. This is SM1 and this is SM2, and to be very precise, these axes actually correspond to the bases that we are having, that is F1T and F2T. I hope that is clear. And if it is clear, then let's start labeling it. So let's start labeling it from here. So this point is 0 0 0 0, and let's vary the LSB for this second point, that is 0 0 0 1. Then let's say this point, the third one, be 0 0 1 1. Then this point here is 0 0 1 0. Then again, now see here, we can't change this place. We have already, if I change this LSB, I'll again get back this. So instead of changing this bit location, I'll make a 1 here. Okay, so what I'll get is 0 1 1 0. Now I haven't received 0 1 1 1, so I can just change only this bit. So what I can get is 0 1 1 1. Then I again haven't received 0 1 0 1, so I can label this as 0 1 0 1. Then again I haven't received 0 1 0 0, so I can just flip this bit. this bit to 0. So what I have is 0 1 0 0. Then I'll make this as 1 1 0 0. Then let's make this as 1 1 0 1. Then this becomes as 1 1 1 1. Then this is 1 1 1 0. This becomes 1 0 1 0. This is 1 0 1 1, 1 0 0 1, and 1 0 0 0. One more thing to note here is there is no strict rule of how we are going to do it, but the only thing that we need to take care is the consecutive bits or the consecutive symbols should vary only by one bit. For example, these two are varying only by one bit. Again, these two are varying only by one bit, that is this location. Similarly, if we look at these two, this one and this one, these two are varying only at these locations. Similarly, you can look for any two bits, any two. Those are varying by only one bit location, like this is varying by only one bit location. So this is the Greek coding for 16 PSK. Any question? Okay, if there are no questions, then let's go ahead. And the next question is, again we need to perform Gray coding based mapping, and now it is a 16 QAM. So basically I have an 8 QAM an 8 pulse amplitude modulation for this vertical, that is quadrature component, and 8 PAM at my in phase component. So as discussed in lecture, what we do is we assign individual labeling. Like we assign first the Greek coding for these levels that are available here, and we assign gray codes for these levels like this. Okay, so let me start doing it. So what we can do is we can label this as 0 0 0. Now again, this is 64, this M is 64, which means that K is log 64 to the base 2, which is 6. And again, on in phase and quadrature component, what do we have? We have on I and Q components, we have, it's a square QAM, so we have 3 bits each. So we need to do gray coding corresponding to 3 bits along this horizontal and the vertical axis, that is the axis corresponding to F1T and F2T, in phase and quadrature components. So for in phase it is 0 0 0 0 0 0, then I have 0 0 1, then it is 0 1 1, then it is 0 1 0, 1 1 0, 1 1 1, 1 0 1, and 1 0 0. And similarly for these components which are along this vertical axis, what do we have is 0 0 0, 0 0 1, 0 1 1, 0 1 0, 1 1 0, 1 1 1, 1 0 1, and 1 0 0. And when we are assigning these and when we are assigning each constellation point, so what we'll do is, let's start with this extreme point here. So the first 3 bits will correspond to this axis, and the next 3 bits will correspond to this axis. So what do we have here is 0 0 0, and then the corresponding one is for vertical axis is this, that is 1 0 0. Then similarly, if we look at, let's say, this point here, so what do we have is corresponding to vertical axis, horizontal axis, it is 1 1 1, and for vertical axis again it is 1 1 1. So similarly, we can repeat the same thing for all the constellation points that are available here. So let's try to do a few. So this one is 001 and 100. Then this is 011, 100. Then it is 010 and 100. Then we have 110, 100, and so on. Then again this point, this one is 001, and the vertical axis is 101, and so on. So you can repeat the same thing and fill up the blanks for all the others. So this is a conventional way of doing these things, and all the things we are doing just to avoid or just to improve the bit error rate, or to be precise, to reduce the bit errors. And these bit errors arise more like one symbol is more likely to get converted or to lie in the decision region of another symbol when they are consecutive, and if they are too far, it's very unlikely, like this symbol will get converted to this symbol with a very less probability, because these two are very far. However, this can get converted to this, and this can get decoded as this. So this is highly more likely compared to this getting decoded as this. And all these change from one to another, like a wrong decoding thing is happening just because there is a presence of noise. And this thing never arose in our analog communication, because we were not doing all this kind of stuff there. Okay, any questions? Okay, let's look at the next question then. So the next question says, is it possible to assign 3-bit data so that the nearest or adjacent points differ by 1 bit only? And we need to determine the symbol rate if the bit rate is 90 Mbps. So let's look at this first part, and this says that we need to basically do gray coding. That is the adjacent points or the nearest points. Now one thing to note here is these two are adjacent and these two are adjacent. Why is it so? Okay, so this thing is something like a 4 PSK, and this thing is also like a 4 PSK. So basically we are having two PSKs, one combined in one plot with different energy levels. Okay, so if we look at the conventional PSK, or let us look at this PSK thing here. Okay, how will the decision regions look? Now note that these points vary based on, or the message signal is carried in phase and not in amplitude or something else for decision regions, and therefore this decision regions should also be depending, or should also be constructed based on the phase. So the decision region for this point here will be something like this. So this region will be the decision region for this. Like if my point lies in this region, then it will be this point. Otherwise it will be something else. Similarly, the decision region for this point, which is here, is basically something like this. Then the decision region for this point will be something like this, and this will be the decision region for this. So these are the decision regions for the first PSK signal that I am having. Now let us look at the second PSK signal that we are having. The second one is having its first point here. So the decision region for this will be this region. Then the decision region for this will be this region. That is this region. Then the decision region for this will be this region, and so on. So basically this decision regions thing is somewhat weird, and there won't be a proper decoding if I consider it in this fashion. Now suppose I reconstruct these decision regions by taking them as an 8 PSK as something like this, like decision region of this point. If I construct it something like this, decision region for this point, if I construct it something like this, then for this point is something like this, then it's like this one, this one, and this one. So now each region, each constellation point has its own decision regions. So now we can clearly see that if my received point lies something here, somewhere here, now there will be a problem. I won't be able to decide it properly. Then this thing will be basically decoded to this and not this. That's why we need to do gray coding like this. Okay, so now again we need to do a 3-bit gray coding. So let's start. We'll have this as 0 0 0, then we'll flip only one bit, that is 0 0 1, then we'll make this as 0 1 1, then we'll write this as 0 1 0. The next thing that we can do is 1 1 0, then we can write 1 1 1, then we can have 1 0 1. I think I made a mistake here. This will be 0 1 0. Yeah, and this one will be 1 0 0. So this is the gray coding that we have achieved. I hope this is clear. Let's go for the next part of this question. So what we are having is, we need to determine the symbol rate if the bit rate is 90 Mbps. So what we have been given is bit rate is 90 megabits per second, and we know that one symbol corresponds to 3 bits, which means that one bit contributes as 1/3 of the symbol. This is symbol per bit, something like this, and therefore the symbol rate is equal to 1/3 of bit rate, which is 1/3 of 90, which is 30 mega symbols per second. Any questions? Okay, if there are no questions, then let us go ahead and look at the next question. So this fifth question says that we need to find the average symbol and bit energy for MPSK, and then we need to find it for MPAM, and we need to find or we need to assume that those are equiprobable symbols. Now before solving this, I'll do a general derivation that will become handy when you have some weird constellation or something like some weird thing that I am having. So we have the signal SMT, and this corresponds to mth log m to the base 2 bit combination. Right, and this SMT, so this SMT, let's say, can be constructed using n orthogonal bases. Okay, so this SMT can be constructed as summation n equal to 1 to capital N Smn phi n of t. We have seen this, or let me use the convention f1 uh, fn t. Okay, this is the representation that we have seen in Gram-Schmidt also. We try to represent it in this form. Okay, so now this SMT is coefficient and this fnt, so basically f1t till fn nt, these are orthonormal bases. Okay, this thing we have seen, we have done this for some constellation. If you observe here, this quadrature amplitude modulation is a two-dimensional signal. It has two bases. One is f1t, which is this, and another is f2t, which is this. And we have represented it as sm1 f1t plus sm2 f2t, which I can simply write as summation n equal to 1 to 2 smn fnt. And in general, if it is an n-dimensional constellation, then this 2 I can simply replace by n. That is the same thing that I am doing here. Okay? Same thing that I am doing here. And we know that energy of the signal is simply integral minus infinity to infinity magnitude of smt square dt. This is the energy. And to be in general, however, this constellation thing is valid only for the signal that I am transmitting SMT is non-zero only for a duration of 0 to capital T, where this T is the symbol duration. Okay, now this I can write as integral 0 to T SMT into SMT conjugate dt. Okay, so therefore this EM is integral 0 to T SMT SM conjugate T dt. And now what I'll do, I'll substitute SMT as this. So this is equal to integral 0 to T summation n1 equal to 1 to capital N Smn phi n t and summation n2 equal to 1 to capital N Smn2 phi n2 t dt. And this I can write as integral from 0 to T summation n1 equal to 1 to capital N summation n2 equal to 1 to capital N, and this is whole conjugate. sm1 sm2 conjugate sorry, this is f not phi fn1t into fn2t dt. And one more thing to note here is that sm1 smn2 smn1 and smn2, these are independent of time, so I can just take it outside and I can bring this integral here. So what I am doing here is summation, changing the order of this summation and integration, something like this. Zero to t fn1t into fn2 into t conjugate dt. Okay, now this quantity, since fn1 and fn2, like this sequence f1 to f capital N, are orthonormal sequences, so this will be equal to 1 if n1 equal to n2, and this will be equal to 0 if n1 not equal to n2. So this integral, in a concise way, I can write it as n1 minus n2 delta n1 minus l2, where this delta is defined something like this. So I can write this integral as summation n1 equal to, let me write it on next page. Yeah, so this em can write it as summation n1 equal to 1 to capital N, summation n2 equal to 1 to capital N, sm n1 sm n2 conjugate into delta n1 minus n2. Now if we consider this thing and apply the shifting property of impulse, this I can write it as sm n1 conjugate delta n1 minus n2. Therefore what we have is summation n1 equal to 1 to capital N, magnitude of sm n1. This SMN1 and this SMN1 conjugate together will contribute to magnitude SMN1 square summation N2 equal to 1 to capital N delta N1 minus N2, and this thing is equal to 1 because summation of impulse over its range will be equal to 1. So my energy is basically N1 equal to 1 to capital N magnitude of SMN1 square, or in simple words this EM is basically summation N equal to 1 to capital N magnitude of SMN square. What does this simplify? What does this signify actually? What is it signifying? So let's look at this PSK constellation. Since it's two-dimensional, it is easier to look at this. We can understand it better. So we know that we have this SM1 and SM2 here, which is given by this formula here. And the energy that we have obtained was this Eg by 2, right? So if we have obtained this energy, which is Eg by 2, let us see if we are getting the same thing with this or not. So we have seen that this energy formula which we had obtained earlier was something like this: summation n equal to 1 to capital N. N is the number of dimensions, and here the number of dimensions for this PSK are 2, so n equal to 1 to 2, magnitude of SMN square. So this is basically magnitude of SM1 square plus magnitude of SM2 square, which comes out to be Eg by 2 cos square theta m plus Eg by 2 sine square theta m, which comes out to be Eg by 2, which is exactly the same thing that we have obtained previously by solving that integral. So now if I have been given a constellation set, and if I have been given these constellation points which are here, and these constellation points basically correspond to the vector that is SM1 comma SM2. So if I know this, I can directly find the norm of each vector and add it, and that will give me my energy. This is the thing that it means actually. So now this geometrical representation actually simplifies. It does not ask us to solve that integral again and again. So I can simply use this formula to find energy, and to be precise, this is equal to 0 to t for our case, magnitude of SMT square dt. This is exactly the same thing. We have started from this equation and we have reached to this equation here. So these two are equivalent, and we can exploit the simplicity of this formula in order to find energies, and we'll do that in coming questions. Okay, yeah. So let's do this now, this fifth question. And what do we need to do in this? We need to find the average symbol energy and bit energy for MPSK and MPAM signals. Okay, so let's do it for MPSK. And just now we saw that this SM is equal to under root Eg by 2 cos theta m and under root Eg by 2 sin theta m, and therefore we know that this Em is basically Sm1 square plus Sm2 square. This thing is Sm1 and the second component is Sm2, and this comes out to be Eg by 2 cos square theta plus Eg by 2 sin square theta m, and this comes out to be Eg by 2. Okay, and what do we need to find is this thing. This Eg by 2 is energy for one symbol. Okay, therefore average symbol energy is given as summation m equal to 1 to m probability of Sm into Em. That is probability with which that symbol, mth symbol, arises. Or let me write it as Pm and Em, and this thing Pm is equal to probability that SMT arises or is sent. And what we have been given is we need to consider equiprobable. For our case, this will be equal to 1 by m. So this formula now reduces to 1 by m summation m equal to 1 to capital M Em, which is equal to, this Em is equal to Eg by 2, and therefore Eg by 2, if I add for m number of times, it will be m Eg by 2 upon m. This comes out to be Eg by 2. Okay, now the next thing that we need to do, okay, so this thing Eg by 2 was the average, was the energy for the mth symbol, and the average energy of the symbol is given by summation m equal to 1 to capital M Pm, which is probability that the mth symbol was sent or mth symbol arises into energy of that symbol. And we have considered all the symbols to be equiprobable, and that's why this probability will be 1 by m, and therefore this thing reduces to 1 by m summation m equal to 1 to capital M Em, and Em is Eg by 2 for all. If I add Eg by 2 for m number of times, it will be m Eg by 2 upon m. Therefore the average symbol energy is Eg by 2, and let me give it some symbol, let's say E average. And now what we need to find is average bit energy, and this is given as average symbol energy upon the number of bits that I am transmitting. So if I have m symbols, the number of bits that I'll transmit will be log m to the base 2. So this comes out to be Eg upon 2 times log m to the base 2. Any questions? Okay, if there are no questions, then let's go to the next question that we are having, or subpart of the same question. So again, we need to find the average symbol energy and bit energy for MPAM, and again we have to assume the equiprobable symbols. Now let's go back to our initial PAM definition, and we have seen that the initial PAM definition, this PAM I can represent it as SMT equal to SM into FT, where FT is the basis vector which is given by given something like this, and SM is under root EG by 2 AM, and this AM is given by this formula something like this. Okay, so now let's try to do this. So if we look at that SM vector which we are having, so it is something like this. This SM only, it is a one dimensional, PAM is a one dimensional signal, and the coefficient that we are having for this basis is SM equal to under root EG by 2 AM. So let me write that. For this PAM signal, SM is equal to under root EG by 2 AM, where this EM is equal to 2m minus 1 minus m into t. And from the formula that we had derived, where em equal to summation n equal to 1 to n magnitude smn square, here we just have one basis, therefore the energy em is equal to magnitude sm square, which comes out to be eg by 2 am square. And therefore, similar to the previous question, the average symbol energy assuming equiprobable symbols will be 1 by m summation m equal to 1 to capital M em. So let me write that also. Average symbol energy E average is 1 by m summation m equal to 1 to capital M em, which is Eg by 2 m summation m equal to 1 to capital M em square. Okay, now let us look at how this em varies. Okay, so if I have m equal to 1, then this E1 is equal to 2 into 1, that is 2 minus 1 minus m into t. So this is basically minus m minus 1 into t. Then if I have m equal to 2, then this is basically equal to 2m minus 4 minus 1, that is 3 minus m. So this A2 is equal to minus m minus 3t, and so on. So if I try to plot it, it will look something like this. So 0, I'll have d, then 3d, then 5d, and so on till m minus 1t. Then I'll have minus d, minus 3d, and so on till minus of m minus 1 t. Okay. So basically this Am is varying from d, 3d, 5d, m minus 1t, something like that, and again in the negative side it is minus t, minus 3d, and so on. Okay, so therefore this E average, this summation in this E average will be summation of this plus this, summation of this square plus 3d square plus 5d square and so on, plus summation of minus d square minus 3d square and so on. Now again if we observe carefully, this m minus 1d whole square is equal to minus of m minus 1d whole square. So this summation in this E average, this summation I can write it as is equal to d square plus 3d square plus 5d square and so on till m minus 1t square plus minus d square plus minus 3d square and so on till minus of m minus 1t square. So therefore E average is equal to this summation, which is Eg upon 2m. Now if we observe carefully, this summation and this summation, these two are same, and this d square is common, so I can write this as 2d square inside the bracket 1 square plus 3 square plus 5 square and so on till m minus 1 square. And you can look at the standard formula. This summation is equal to m into m square minus 1 by 6. This is a standard formula that you can look into some book, and this comes out to be Eg d square by m into m square minus 1 by 6. So this comes out to be Eg m square minus 1 d square upon 6. So this is the average energy for this quantum signal and symbol energy, and average bit energy is equal to this average symbol energy upon log m to the base 2, and this comes out to be Eg m square minus 1 d square upon 6 log m to the base 2. Any questions? Okay. If there are no questions, then let's look at the sixth question. So what we have been given is, consider the following 8-point constellation. The nearest constellation points in this 8 column are separated by A units, and we need to find A, B, average symbol energy and average bit energy. Okay, so what it is being said is, we have 2 points here. Hello? Am I audible clearly now? Okay, can you just check the stability of your internet connection? Because I didn't get any notification that my network is poor till now. Yeah, okay, thanks. Yeah. So what it is said is the nearest nearest neighboring constellation points are separated by a distance of a. That is, this distance is a, and this distance is also a. And again, this distance is also a. This one. This is what is being given. Like these are equidistant. Okay. That is the meaning of this point here. That is the nearest neighbor constellation points in it QAM are separated by A units. And what do we need to find? We need to find the value of A, B, and average energy, average symbol energy, and average bit energy. Okay. Yeah. So let us first try to find A. And for that, let us consider this triangle here. This triangle which I have highlighted. We know that this point will be A and this point will be A. And this is capital A. So simply what do we have is a square plus a square, small a square is capital A square. Therefore 2a square is equal to a square, and therefore a is equal to a upon under root 2. Is it clear? This is the first thing that we are having. This is simple. And okay. Okay, and the next thing that we need to find is this B. So let us look at this triangle. This is B. This is B. This is capital, sorry, this is capital A, and this is small a. Let us look at this triangle. Okay, let me draw it. This is some out of scale. This won't be an obtuse angle. It will be an acute angle only. So, yeah, this will be something like this. This will be B. Then I have this something like this, A, and this thing will be small a. Okay, and I need to find B. So let me drop a perpendicular from here on this. Okay. Just a minute. Yeah. So this is what we are having. Or okay. Just for the sake of simplicity, I can also draw this as something like this. This is B. Then I have something like this, that is A. This is A. This is B. Then I have drawn this A. And then this side will be capital A. And again note that this angle is 45. This symbol is located at 45 degrees. Okay, it is equidistant, like it is proper spacing. Okay, so this angle that is between A and B, this is 45 degrees. and let me drop a perpendicular here, and let's say this is x, this will also be x, and let's say this is y. And what do we have is b is equal to x plus y. Let me number it as second. Okay, so now what do we have is this a is basically x cos 45 degree. I want to find this b. It's easier to find this x and then find this y. This y is the base of this right angle triangle. I can use Pythagoras theorem once I know this x. And this x, these two sides are same. So once I know this x, I can easily find this y. And this b is equal to x plus y. Another way to do is you find this angle theta and then apply cosine rule. These are the two approaches that you can take up. I hope that answers your question. So this a, so where were we? This a is equal to x cos 45 degree, or this a is equal to x sin 45 degree. Sin 45 cos 45 both are 1 by root 2. So this is a equal to sorry this x is equal to a cos 45 degree. So this comes out to be a by root 2. So this is basically x by equal to cos 45. So this x is equal to a by root 2, and therefore this y will be equal to a square, or let's say this y will be equal to a square minus x square under root, which is equal to under root of a square minus a square by 2. And note that a square is equal to capital A square by 2. So this I can replace as a square minus capital A square by 2, and that's why it becomes capital A square by 4. So what do we have is this y is equal to under root of a square minus capital A square by 4. This is equal to under root 3a square by 4. This is equal to a by 2 root 3. Now what do we have? We have this b is equal to x plus y. We have this b as x plus y, and therefore this b is equal to x plus y is equal to x is equal to a by root 2 plus y is equal to a by 2 root 3. Again this a was capital A by root 2, so I can write it as capital A by root 2. Root 2 into 2 root 2 into root 2 is 2, so this is, so this comes out to be a by 2 into 1 plus root 3. So what do we have? A is equal to a by root 2 and b is equal to a by root 2, sorry, a by 2 into 1 plus root 3. Okay, so this is what we are having right now. Okay, so what we are having is a equal to capital A by root 2 and b equal to a by 2 1 plus root 3. So we have found out this a, this b, and next thing that we need to find is this average symbol energy. So this average symbol energy will be energy of this plus this plus this plus this plus energy of this plus this plus this plus this whole divided by 8. Now observe, this thing is one PSK and this thing is something like another PSK, right? So, and we have seen that energy of a PSK constellation is basically equal, any PSK constellation point is basically equal to the energy of this, or energy of total energy or total average energy of entire PSK constellation is radius of this. So if I consider the energy of these 4 points, these will be A. That is energy of this point, this point, this point and this point. These will be A square. And energy of this point, this point, this point and this point will be B square. Okay. So let me mark it something like this. Average symbol energy is equal to A square plus A square plus A square plus A square, and average symbol energy for these 4 will be B square. So plus B square, B square, B square plus B square, and this whole thing is to be divided by 8. So what do we have is 4A square plus B square upon 8, that is A square plus B square upon 2. A square is A square by 2 and B square is A square by 4 inside the bracket 1 plus root 3 whole square upon 2. Okay. I can take out A square by 4 common, so this becomes A square by 4 into 2 from this denominator. 2 plus, I can just open this square term, so this will be 1 plus 2 root 3 plus 3. So this comes out to be A square by 8, and then it is 6 plus 2 root 3, and this comes out to be A square by 4, 3 plus root 3, or I can write this as 3A square by 4. This is root 3. Sorry, 1 plus 1 by root 3. Okay. Yeah. So this is the average energy per symbol, and next thing that we need to find is E average bit, that is average energy per bit, and this is equal to E average upon log m to the base 2, that is 3A square upon 4, 1 plus 1 by root 3 upon log 8 to the base 2. Now this quantity is equal to log 2 cube to the base 2, which is equal to 3, and this 3 and this 3 gets cancelled. So what we are left with is A square by 4 into 1 plus 1 by root 3, and this thing is basically average I think you got confused with my notation E average comma B. that B was corresponding to bit. So we need to find average bit energy. This B, this B is simply the radius of this. It has nothing to do with your bit. Is that what you wanted to ask? Oh, okay. Let me know once you are done. Okay. So if there are no doubts, then these are actually not big. I don't think these big questions will be asked. If it is MCQs, it will be somewhat similar to what you're having in your assignments. But these big questions might be asked in your college exams. These kind of questions are asked in GATE also. These kind of questions are asked in GATE. The first question which I had covered today, you were not there. That was from GATE 22. The very first question which I took today. And yes, this kind of questions have been asked in past GATE exams. So yeah, may not be in for this particular course, but these will be useful when you handle your course in your college or when you handle the competitive exams like GATE. It will just build your understanding and how to handle these kind of questions. That's the whole role of this tutorial. Yeah. So let's go ahead with the next question. So we need to find, so what is given is the nearest neighbor constellation point in this 8 PSK is separated by A units. That is this distance. This distance is A units. And we need to find R, average symbol energy and average bit energy. Same thing. Now if I draw this triangle from here and like this, yeah, this is R and this is R, and this angle here is 45 degrees. Okay, now we can apply cosine rule for, let's say, DEF, triangle DEF, and angle as 45 degrees, that is with respect to this angle, which means I'll be having equation for this A square. So what I'll have is this capital A square will be sum of other two sides square, that is R square plus R square minus 2R square cos 45 degree. Okay, so this is 2R square common, 1 minus, or let me not take this let me just take this R square common, 2 minus 2 into 1 by root 2, which is equal to R square 2 minus root 2. Therefore this R is equal to A upon under root of 2 minus root 2. Now again, this E average, that is average symbol energy, we had seen that this will be r square plus r square 8 times whole divided by 8. So this will be simply equal to r square, which is equal to a square upon 2 minus root 2, and this average bit energy will be equal to E average. Again, this is 8-point constellation, which means that log 8 to the base 2 will be equal to 3. So this is upon 3, and this comes out to be a square upon 3 multiplied by 2 root 2. Any questions? Okay, if there are no questions, then let us go ahead and look at the next question that I am having here. So it says that consider the 2-point constellation. Yeah, consider the 2-point constellations as below. So these are the two 8-point constellations that we are considering, and the minimum distance between two adjacent points is 2a. That is, this distance is 2a, this distance is 2a, this distance is 2a. Also here, this distance is 2a, this distance is 2a, this distance is also 2a, this distance is 2a, this distance is also 2a. Okay, and next thing that we need to find is we need to determine the average transmit power for each, assuming equiprobable signal points, which is more power efficient. So we need to find average transmitted power for each of this constellation. So let us first do that. So let us first do that for first constellation that we are given here. So if these are the constellation points, and each axis corresponds to one basis, and therefore these points are basically coefficients of those bases, and we have seen it earlier. Yeah, we have seen it earlier that this EM energy of each constellation point is simply summation of each constellation point's energy, or the coefficients of each basis, okay, corresponding to that constellation point. So if we know the coordinates of these points, if we know the coordinate of these points, the energy of this point will be simply equal to the L2 norm, or basically element wise square of that coordinate. Like if it is x comma y, then energy of this one will be x1 square plus x2 square, that we had seen earlier. So now let us just find out the coordinates. What we have been given is these adjacent points, and the adjacent points are separated by 2a distance. This we know. Okay, so if we know that, then this will also be 2a, which means this distance will be a, and this distance will be a. Okay, and similarly we know that this distance is 2a, right? So let's try to find out the coordinate of this point. So this is basically 2a comma a. Then the coordinate of this point, I'll just remove this. The coordinate of this point will be 0 comma a, and coordinate of this point will be, this distance is 2a, so this will be minus 2a comma a. Okay, now let us do this one, these ones. So now these are just flipped one, that is, instead of a I'll be having a minus a. So this is minus 2a comma minus a. This is 0 comma minus a, and this is 2a comma minus a. Now let us look at this point. This is basically, this distance is 2a and this distance is a. So this is 0 along horizontal axis, and along vertical axis it is 3. So this coordinate is 0 comma 3. Okay, and this coordinate will be 0 comma minus 3a. Right. So E average will be equal to E1 plus E2 plus E3 plus E4 plus E5 plus E6 plus E7 plus E8 whole divided by 8. And let me number these also. Let's say this is 1, 2, 3. Let me start it from top. Yeah, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is equal to, E1 will be equal to 0 plus 9a square. E2 will be equal to 4a square plus a square, plus E3 will be equal to 0 plus a square, plus E4 will be equal to 4a square plus a square, plus E5 will be equal to 4a square plus a square. E6 will be equal to 0 plus a square. E7 will be equal to 4a square plus a square, plus E8 will be equal to 0 plus 9a square. And this whole thing is divided by 8, and this comes out to be, this is 9a square multiplied twice, so this is 18a square. Then we have this 5a square, 5a square, 5a square, 5a square. So this is basically 20a square, plus we have a square plus a square. So this is 2a square upon 8, and this comes out to be, this is 20 plus 20, 40a square upon 8, which is equal to 5a square. Okay, this is the first thing that we are having here. This is for the first constellation that we are having. Now let us repeat the same thing for our second constellation. So again, what we are having is this, okay, yeah, this distance is A, this distance is A, this distance is A, and this distance is also A. So now we need to find what is this distance, that is x. So this x, this x will be a square minus a square by 4. Right, this a square minus a square by 4, this comes out to be 3a square by 4. This is x square that I am having. Okay, so what basically we are having is, this is a, this is root 3 by, or let me write it as x only, just for convenience, notational convenience. And this thing is also a, this horizontal thing is also a, and so on. Okay, so now let us write the coordinates of these. So the coordinate of this point, the coordinate of this point will be a comma, or rather minus a comma x. The coordinate of this center point will be 0 comma x. The coordinate of this point will be a comma x. The coordinate of this point will be minus a comma 0. Coordinate of this point will be a comma 0. Then coordinate of this point will be minus a comma minus x. This is 0 comma minus x, and this is minus a comma minus x. Okay, so let's solve this. E average will be again e1 square plus e2 square plus e3 square plus e4 square plus e5 square plus e6 square. And let me write this as b. We are finding for b. This is a. Let's say this is a plus e7 square plus e8 square. So this e1 square, let me number it as 1, 2, 3, 4, 5, 6, 7, 8. So this e1 square will be a square plus x square. This e2 will be x square plus e square plus x square plus e square plus e square plus e square plus x square plus x square plus e square plus x square. So this comes out to be 1, 2, 3, 4, 5, 6. So this comes out to be 6a square plus 1, 2, 3, 4, 5, 6 plus 6x square. Okay. So this I can write as this is equal to 6 times a square plus 3a square by 4. So this is equal to 6 into 7a square by 2. 7a square by 4. This is 21a square by 2, and this comes out to be 10.5 a square. Now clearly this a part was having energy as, oh yeah, and this whole thing has to be divided by 8. This whole thing is divided by 8. It's divided by 8 into 8. This is divided by 8. So this is 10.5 by 8 that we are having here. Just a second. Yeah. And this comes out to be 1.3125 a square, and this is less than e average a, and hence this constellation is more power efficient. I hope this is clear. Any questions? Okay, if there are no questions, then let's go ahead for the next question. So what does it say is we need to use Gram-Schmidt orthogonal Gram-Schmidt procedure to find MPAM signal. Okay, orthogonal basis for MPAM. Okay, so what do we have here is this SMT for any MPAM signal is basically equal to AM GT cos 2 pi FCT, right? And we have seen that the energy for this is equal to Em square Eg by 2. Now this Gram-Schmidt procedure, let's start from this mth point only. So let's say Fmt is equal to, yeah, this is Fmt is equal to Smt upon root Em, and this comes out to be Emgt cos 2 pi Fct upon under root Em square Eg by 2. So this comes out to be under root 2 by Eg Gt cos 2 pi Fct. Okay, now let us consider another signal, that is Snt, such that n is not equal to m. Okay, so if we need to find Fnt, this will be equal to, this is any arbitrary n, and n comma m belong to 1 2 till capital M. Okay, now I have this Fnt with me. Yeah, so this Fnt will be Snt minus inner product of Snt with Fmt multiplied by Fmt. So now let us focus at this Snt inner product with Fmt, and this comes out to be 0 to capital T Snt Fmt dt. This is equal to 0 to T Amgt Ant cos 2 pi Fct dt, multiplied by under root 2 Eg Gt cos 2 pi Fct dt, and this is equal to En under root 2 by Eg. Inside the bracket, this will be T G square T 1 plus cos 4 pi Fct by 2 dt, and this comes out to be En 2 by Eg inside the bracket. This first integral 0 to T Gt square will be equal to Eg, so this is Eg by 2, plus we assume that this Gt is very slowly varying, and that's why we can ignore it. It won't be affecting much, affecting this cos 4 pi Fct much. So this integral, the second integral 0 to T cos 4 pi Fct, this will be approximately 0. So this is equal to 0, and this comes out to be Em root Eg by 2. This is not Em, this is En. Okay. Yeah. So what we are having here is Fnt is equal to Snt minus En root Eg by 2 into Fmt, and this comes out to be Snt is En Gt cos 2 pi Fct minus En under root Eg by 2 multiplied by under root 2 by Eg Gt cos of 2 pi Fct, and this comes out to be 0. therefore for all n not equal to m, fnt is equal to 0, and we have fmt is equal to under root 2 by eg gt cos 2 pi fct, and this is the only basis for MPAM, and therefore this is 2D signal. Sorry, not 2D. This is one-dimensional constellation. Since it has only one basis. Any questions? Okay, if there are no questions, then let us go ahead with the last question that I wanted to cover today. And it is also very similar to what we have solved in previous thing. And this says that we need to use Gram-Schmidt procedure to find the basis for this MPSK. Okay. Yeah. So for MPSK, what do we have is this SMT. So for MPSK, SMT is equal to GT. Let me write it from new line. It's a big equation. GT cos theta m cos 2 pi fct minus GT cos theta m cos 2 pi fct minus GT sin theta m sin 2 pi fct. So this is what we are having. So let us take S1t. So if I am having S1t, that is m is equal to 1, then it implies that what we are having is, yeah, this theta m is equal to m minus 1 pi by m. So this theta m, or rather theta 1, will be equal to 0. So this S1t will be equal to GT cos 2 pi fct, and we know that another thing that we know here is basically this energy Em is equal to under root, or sorry, is Eg by 2. This we had already seen in the lectures. So this is S1t. So therefore the first basis vector F1t will be equal to S1t upon under root Eg, and this comes out to be not Eg, Em, or rather E1, and this comes out to be under root 2 upon Eg GT cos 2 pi fct. This is the first basis vector that we are having. Okay. Now let us look at the second basis vector that we need to see. Okay. So what we'll do is, let's say this m is equal to, let us take a special case. We know that Gram-Schmidt orthogonalization procedure, Gram-Schmidt procedure, we can apply to all the vectors or all the signals in any sequence. So for the second basis, let us choose a particular m which is equal to m by 2 plus 1, and for this my theta m will be equal to it will be m minus 1 upon m pi. So this will be equal to m by 2 plus 1 minus 1 by 2 pi. This is not 2 pi, m pi, and this comes out to be pi by 2. So if that is the case, then for this thing SMT will be equal to, and let's say I give it SM hat T, this is theta m hat, yeah, and this thing will be equal to, now theta m is pi by 2, so this first term which corresponds to cos theta m will go to 0 and this term only will prevail. That's why we chose this particular term, so that I can get this theta m as pi by 2. You can take theta 2, this m as 2 and proceed, but that will be a little bit complicated operation. So let's go with the simplest case where this m is this m hat is capital M by 2 plus 1, and this theta m hat is m hat minus theta m hat is coming out to be pi by 2. And for this, what we are having is, for this case, this is gt sine 2 pi fct. Now again this SM hat is having only gt sine 2 pi fct, and we have this EM is equal to 0. Okay, now let us apply Gram-Schmidt step. So this f2 tilde will be equal to, this is intermediate function, it is not my final basis. So this f2 tilde will be equal to SM hat t minus inner product of SM hat t f1t multiplied by f1t. Okay, so now let us look at this inner product of SM hat t comma f1t, and this comes out to be integral 0 to capital T minus gt sine 2 pi fct multiplied by 2 by under root of 2 by eg gt cos 2 pi fct dt. This comes out to be in minus root 2 by eg integral 0 to t g square t. This is sine 2 pi fct multiplied by cos 2 pi fct. So this I can write as sine a cos a is basically equal to sine 2a by 2. So this comes out to be sine 4 pi fct whole divided by 2. So this is equal to minus 1 upon under root 2 eg integral 0 to t, and this fc is very high, and corresponding to this gt is very slowly varying, and that's why what we can do, so basically this gt is some sort of an envelope. So this gt is varying like this, and this carrier is varying like this 2 pi fct is varying like this. So this means that this gt is basically not changing my nature of sine that much. So I can approximate this gt as not affecting anything. So this is approximately equal to sine 4 pi ct, and this t is basically some integral function of k by t, so this goes to 0. Okay, so this inner product is equal to 0. So this f2 tilde t that we are having is basically coming out to be as SM hat t. Okay, now therefore the second basis f2 hat f2 t will be equal to SM hat of t upon energy of this signal, and energy of this signal will be basically EM hat, and this is equal to minus gt sine 2 pi fct whole divided by under root eg by 2. This is under root, so this comes out to be minus under root 2 eg gt sine 2 pi fct, and this is the second basis vector that we are having, and the first one which we had obtained was this one. Yeah, so this was 2 by under root 2 by eg gt sine cos 2 pi fct, and this is the basis, these are the two basis vectors which we had obtained. Now are there more basis vectors corresponding to this PSK? So what we'll do is, let us consider M such that M is not equal to 1 and M is not equal to M hat, and we know that this SMT will be equal to GT cos theta M cos 2 pi FCT minus GT sin theta M sin 2 pi FCT. Okay. Yeah. So now let's try to construct the third basis, that is F3T, using this SM. So SM, this will be, or we'll have first this intermediate signal, that will be SMT minus inner product of this SMT with F1T along F1T minus inner product of SMT F1T, sorry, not F1, F2T along F2T. Okay. So now let us try to find SMT inner product with F1T. So this is equal to integral 0 to T. SMT is this quantity, that is GT. I can take this GT outside, this is common. GT cos theta M cos 2 pi FCT minus GT sin, sorry, no GT, I have taken it common, sin theta M sin 2 pi FCT, and the first basis is under root 2 EG GT cos 2 pi FCT. So this will be multiplied by under root 2 EG GT cos of 2 pi FCT dt. Okay, so this is equal to under root 2 EG integral from 0 to T GT square, can take this and multiply, so this will be cos square 2 pi FCT, and this is dt multiplied by cos theta M minus under root 2 by EG integral 0 to T G square T cos 2 pi FCT sin 2 pi FCT multiplied by sin theta M dt. So let me write it again, it was so much cluttered there. Inner product of SMT, so this was under root 2 by EG cos theta M integral 0 to T G square T cos square 2 pi FCT dt minus under root 2 by EG sin theta M integral 0 to T G square T cos 2 pi FCT multiplied by sin 2 pi FCT dt. Now we have seen here that this integral, that is G square T. So if I rewrite this integral, this is basically equal to minus root 2 by EG integral 0 to t g square t sine 2 pi fct multiplied by cos 2 pi fct dt, and we have shown that this integral is equal to 0. So same way this integral will be equal to 0, and similarly in our previous question, in this previous question we had shown that this integral, that is g square 0 to t g square t cos square 2 pi fct, this integral comes out to be eg by 2. Okay, so this integral comes out to be eg by 2. Or to be precisely previous question. Okay, so now this comes out to be under root 2 by eg cos theta m and multiplied by eg by 2. So this comes out to be eg by under root eg by 2 cos theta m. Okay, so this is the first thing that we have found out. So now let us find out inner product of SMT with F2T. So this comes out to be integral 0 to t SMT is same thing, we write it from second line, 0 to t gt, inside the bracket it will be cos theta m cos 2 pi fct minus sin theta m sin 2 pi fct, whole thing is getting multiplied by minus under root 2 by eg gt sin 2 pi fct dt. So this comes out to be minus under root 2 by eg cos theta m integral 0 to t g square t cos 2 pi fct sin 2 pi fct dt plus under root 2 by eg sin theta m integral 0 to t g square t, and we have sin square 2 pi fct, so this I can write as 1 minus sin, sorry, not sin, cos 4 pi fct by 2. And again we had seen that integral 0 to t g square t cos 4 pi fct, this integral goes to 0. So basically this value is equal to integral 0 to t, or it's approximately equal to this dt by 2, that is equal to eg by 2, and again this thing goes to 0, we have seen earlier. So this thing is now equal to under root 2 by eg sin theta m multiplied by eg by 2, which is equal to under root eg by 2 sin theta m. Okay, so now let us go back to this equation which we had written for f tilde t. So this is what we are having. Let me copy paste it there. So we are having this thing. So let us write down what is our SMT. So SMT is gt cos theta m cos 2 pi fct minus gt sin theta m sin 2 pi fct. So this thing is my SMT. Let's see, this is, we are having this as this inner product SMT into F1T. SMT into F1T is under root Eg by 2 cos theta m. So this is under root Eg by 2 cos theta m, and F1T was under root 2 by Eg gt cos 2 pi fct. And let's see, this is, yeah, minus this term SMT, this inner product was again under root Eg by 2 sin theta. So this is under root Eg by 2 sin theta m multiplied by minus under root 2 by Eg gt sin 2 pi fct. Now if we observe carefully, this term gets cancelled, so this term and this term are exactly the same, and similarly this term and this term are exactly the same. These both are of opposite signs, so they both cancel out each other, and therefore this f tilde 3 is equal to 0 for all m not equal to 1 and m not equal to m hat. Which means if I consider any other signal other than that m, for m equal to 1 and m equal to m hat, that is when the angle was 0 or when the angle was pi by 2, for all others now this intermediate signal for the third basis comes out to be 0, which clearly means that no more orthogonal or no more basis vectors signals, not vectors, signals are present. So let me summarize it. Therefore, for MPSK, using Gram-Schmidt procedure, the two bases are F1T is equal to under root 2 by Eg gt cos 2 pi fct, and F2T is equal to minus root 2 by Eg gt sin 2 pi fct. And this is the same thing that we had seen in our earlier discussion. So this is the answer for the question that we were looking for, and this was the last question that I had planned to cover today. That's all the content that I had planned to cover today. If you have any questions, feel free to ask right now, or you can make use of the question answer portal that you are having for your on your NPTEL course website. If you have no further questions, you are free to leave the meeting. Thank you for attending today's session.